Hello, everyone. Welcome to today's class. And today we'll start to talk about unsupervised learning. And we will use two lectures to talk about it. And in the last lecture, we probably will talk about one example of unsupervised learning. Okay. All right, let's start from part one, clustering. So now we are here, okay, unsupervised learning. So first, let's review what's the difference between unsupervised learning and supervised learning. So in an unsupervised learning problem, there is no response variable. So we only have a bunch of feature variables, X variables. And the goal usually is to understand the relationship among them, among these observations. Try to figure out some patterns or clusters or some unknown features. Okay. So they are called unsupervised learning algorithms because there is no Y variable to supervise the learning process. So no Y variable to guide the process. So that's why it's called unsupervised learning. Now let's first take a look at clustering. So clustering is used to identify different groups of similar objects in a multivariate data set. Multivariate means there are many features in the data set. There are a lot of different types of clustering strategies, like partitioning methods, hierarchical clustering, density-based clustering, etc. But in our class, we will only focus on the first two methods, partitioning methods and hierarchical methods. So start with partitioning clustering. So this clustering method subdivides the dataset into a set of K groups, where K is the number of groups pre-specified by the analyst. So if we want to use partitioning clustering, we need to first decide how many clusters are needed. So probably we need to visualize the data and guess how many clusters there are in the observations. There are two main methods. The first one is called K-means clustering, and the second one is called K-meadows clustering. And K-means was invented earlier in 1967, and K-meadows was invented later in 1990s. They are kind of similar, we will see. Let's first take a look at K-means clustering. So each cluster is represented by the center or mean of the data points belonging to the cluster. So the problem is basically finding the cluster centers. And then given a new observation, you will allocate the new observation to that cluster based on where the center is. So the main goal is to figure out the centers of those clusters. And K-means algorithm measures distance between points with the Euclidean distance by default. Because all of these calculations depend on the distance. Right? So how to measure distance by default, the K-means method uses the Euclidean distance. For example, if we have two-dimensional data, the distance between 2 points is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, the straight line distance. This is a Euclidean distance. Right? And K-meadows algorithm measures distance between points with a generalization of the Manhattan norm or L1 norm. So this is the default behavior of the K-meadows clustering. However, the key difference between these two is not related to the metric that is used to calculate the distance. It depends on something else. Okay? But what is Manhattan norm or Manhattan distance? It is the straight line distance. So it is the sum of these two edges in the triangle. That's the sum of these two. X1 minus x2 plus y1 minus y2, absolute values. Okay? And the most common algorithm in the K-Medois clustering method is partitioning around Medois or the PAM method. And they have their strengths and disadvantages. So the K-means method is more sensitive to outliers just because of the metric, and also it relies on the mean of each feature variable. And K-Medois is more resistant to outliers. Consequently, it is less sensitive to outliers because it relies on medians, the median of each feature. And also the metric is also more resistant to outliers. All right, let's take a look at K-means first. So this one is an algorithm-based approach to find K clusters in the data set. It uses a heuristic update strategy to make clusters as far as possible and each of the clusters as tight as possible. So at the same time, they want to make clusters as far as possible, the distance between any two clusters as far as possible, and at the same time, make each of the clusters as tight as possible. So namely, try to reduce the radius of each cluster, the area of each cluster. The smaller, the better. So it is not an exclusive method. Namely, it cannot consider all of the possible clustering ways to cluster these observations. It's because it is just the computation load is too heavy. For example, suppose we have 25 observations in the training data set, and we want to cluster them into 4 clusters, okay, K equals 4. Then let's see how many possible ways to cluster these 25 observations. Okay. So let's use 4 cells to represent the 4 clusters. 1, 2, 3, 4. Okay. Then take the first observation. How many ways to assign the first observation? Consider X1. How many ways to cluster the first observation? It can be put in cluster 1, 2, or 3, or 4. So 4 ways to do so, right? And then the second observation, same thing. You also have 4 options to cluster X2. Totally 16 ways already, right? And consider all of the observations. Suppose we have n observations. Then you need to multiply for n times. So totally n of them. Then it will be equal to 4 to the these many ways. If n is 25, then it's equal to 1.259 times 10 to the 15. So this is a total number of ways to cluster 25 observations into 4 clusters. So you see, it's impossible to consider all of these possibilities. Instead, it will do it in a more like heuristic way or greedy way, and the algorithm will stop at some local optimum. And it must stop, otherwise it will take forever to finish the whole searching process, right? And the K-means algorithm actually uses this heuristic method. So let's see how it works. The algorithm iteration begins with an initial guess for the K cluster means. So basically, at the beginning, it will randomly choose K centers for the K clusters. It's purely random. And then for each observation, cluster it to the closest center, right? Cluster center. And then after that, after each observation is clustered, we will update the center, the cluster centers, namely recalculate the cluster centers, calculate the mean of each dimension. And then in the next iteration, we will for each observation cluster it to the closest mean again. So let's see one example. Suppose we have two-dimensional data. The scatter plot looks like this. And at the beginning, the algorithm will randomly pick three centers. One, two, three. Suppose we want to cluster the data into three groups. Okay. And these 3 points are just totally randomly chosen. Okay? And they are not belong to the data set. Remember that. Okay? So these are just 3 random points in the two-dimensional plane. Okay? And then for each observation, we calculate the distance. For example, let's consider this point. Let's consider this point. We calculate the distance between the point and each cluster. And since this point is closest to this, let me see. So calculate the distance between the point and each center. And since the point is closest to this one, this is chosen as the center for this point. So the point is clustered to this center. We do the same thing for all of the observations. And then the first iteration is done. So you see after the first iteration, these points are clustered to this center. We can call it A, B, and C. So all of these red points are clustered to center A, and all of these green points are clustered to center B, and then these blue points are clustered to center C. And then we update the centers, namely we recalculate the center for each cluster. So then you see cluster A, the center is here, and C is here, slightly changed, but B, the center of cluster B changed a lot, from here all the way to here. So this is a updating process. And then assign observations to the centers again, the closest center again. So the program will stop when it's not necessary to reassign observations anymore. Well, let's see some terms. In math and physics, the centroid or geometric center of a plane is the arithmetic mean position of our observation in the figure. So for two-dimensional data, so they are basically x bar, x1 bar, and x2 bar. So for example, this is x1, this is x2. And the center is the mean of each dimension. It's called the centroid or geometric center. So this is another example with a different initial. So see in this case, the first two centers are clustered together, very close. And then the third one is here far away from them. Okay, then this is the initial assignment, and update the centers, and then assign observations again based on these updated centers. And this is yet another initial. So these are the first 3 centers, 1, 2, and 3. Initial assignment, update the centers, and then reassign. Let's see one example. We will use the faithful data set. So this data set contains the eruption times in minutes and the waiting times to the next eruption in minutes for the old faithful geyser in Yellowstone National Park. So it only has 272 observations and 2 columns. The first column is eruption time in minutes, maybe 3.6 minutes or 1.8 minutes, etc. And then the waiting time to the next eruption. So the waiting time is much longer, apparently, right? So so both of these two are feature variables. So we'll treat them as feature variables. So let's take a look at the data first. So from the scatter plot, we can tell that there probably are 2 clusters. Very obvious, right? So based on the density of the points, there should be at least 2 clusters, right? Corresponding to longer waiting time and longer eruption time and shorter waiting times and shorter eruption times. Okay. And then for very simple data sets, okay, like the faithful data set, it's easy to identify how many clusters are needed. Easy to tell by visualizing the data. However, for high dimensional data or for data sets that are more complex, it's very difficult. Sometimes it's very difficult to figure out how many clusters are needed. So there actually is a package which can help us to identify the optimal number of clusters that are needed. So the package is called Fractal Extra. If you want to play with it, yeah, please install it. Okay, you need to install it because so this part will be covered in your exam too. So you definitely need to install it first. And the function we use is this function. Just input the data set and then specify the method that we want to do clustering and calculate how many clusters are needed and specify the method. So here we use gapstat. There are many methods that can be used. For details, check this link. Check this link. So this is an essay about an article about this package. So we just chose this gap statistic. The larger the better. The larger the better usually. So this is a result. This it identifies it illustrates the best option using this dashed line. So apparently for our faithful data set, the optimal K is 2, which is consistent with our expectation. There should be 2 clusters. It seems that the K with the largest gap statistic should be chosen. But actually, the algorithm does not strictly follow that strategy. The strategy is that the optimal number of clusters is the smallest value of K such that the gap statistic is within 1 standard deviation of the gap at K plus 1. So namely, we try to find K such as gap K is greater than or equal to gap K plus 1 minus the standard error of the gap K plus 1. Okay. So see, for example, here, so this is gap 3, right? This point is gap 3 minus standard deviation of gap 3. Okay. So this point is greater than the lower limit, right? Lower 1 standard deviation limit, okay? Greater than the G2 is greater than G3 minus standard error of G3. Right? So, and this is the smallest K that it happens, right? If you observe the plot, you see this one won't work, right? K equals 1 doesn't work because it is not greater than this, okay? So that won't work. However, this point is also greater than G4 minus standard deviation of G4, right? However, this is not the smallest k that this inequality happens, this inequality is true. The smallest k is 2 when this inequality is true. Is satisfied. And so that's why the optimal k is 2. It's not 3 or any other of them. Okay. So basically, we follow the principle of parsimony. Try to build the simplest model such that the data can be explained or modeled well, like the simplest model. So the smaller the number of clusters, the simpler the model. So we choose the smallest k that this is true. Okay. All right, so this is how we find the optimal k. And then we know that the optimal k is 2. We can apply the k-means method. So R has this genetic function in base R, k-means. You just need to specify the data matrix and how many centers you need. And save the result here. And then this result is a list. Again, it has different components. The centers components contains the coordinates of the two centers. So the first center is at 4.22979 and 80 something. So the eruption time is 4 point something, and waiting time is 80 something. So it's corresponding to a center here for this cluster 1. And the other one is 2.1 and 54 something. So it's somewhere here, the other center. Okay. So this is one component of the output. And you can also take a look at the cluster labels. So this cluster component contains the labels. Since there are only 2 clusters, the algorithm assign 1 and 2 to the clusters. And this plot, and then we pull out we add the cluster information to the original data set and create this scatter plot. So basically, we map the cluster label to color. You see, it looks pretty nice. All right, so this is the first try. However, notice that the 2 variables have very different scales, right? If we take a look at this scatter plot, see waiting time is from about 40 to 100, but the eruption time are single digits, from 0 to 6 minutes. And because the k-means method highly relies on distance, it's very sensitive to distance. And the distance is very sensitive to the magnitudes of variables. It's better to scale the data before we apply the k-means algorithm. So that's why we first should scale the data. The generic R function scale can be used to scale the data. So it will minus the mean and divide it by the standard deviation. So x j minus x. So x bar divided by s. For each column, it will standardize the data. And then we apply the k-means function again using the scaled data on the scaled data. And then the centers will be different, coordinates will be different, and the plot looks slightly different too. So now, if we draw a border for the classroom result, so it's somehow like this. You have 2 ellipse areas instead of previously, the data is separated in this way somehow. Like you have two rectangle areas. All right. And an alternative way to do the scatter plot is to use this function, uh, favorite cluster function. Also, this function is building the package that we use to figure out the optimal number of k. Right? So, so this function is kind of more flexible. You can draw the borders. You can choose the shape. So, for example, I choose convex, and so then we see this kind of convex polygon drawn up around the two clusters. And also, you can choose the palette, and you can also it also just use the observation index to label each observation. So this is particularly useful to identify the observations in the border area, in this area, and identify the differences using different strategies. For example, this first data plot, actually, this first plot is about the result using unscaled data. You see, we use KM mod 1. So this one does the data is the raw data. It looks like this. If we use scale data, KM mod 2, as you see, it looks like this. It's more like ellipse shapes. And notice that there is an argument called stand. So stand is a logical variable. If it is true, then in the plot, both x and y variables will be standardized. So you won't see the original values of the two variables. So, although the algorithm might have standardized data, however, the plot will show it. So you see this one. Although when we fit mod 2, we scale the data first. But if we choose stand equals false, we still can see the original values for x and y, although the method used to scale data. So this one is better than this one. You see the difference between 211. Original was cluster 2, but now it's in cluster 1. All right. So that is k-means method. Okay. And the second method is k-medoids. K-means relies on means, right? The mean of each feature. And now k-medoids. So what is a medoid? A medoid can be defined as the object of a cluster whose average, the similarity to all objects in the cluster is minimal. So it is kind of like it's a point in the cluster. First of all, it is a point in the cluster. It's one observation in our cluster. And it is the sort of the median, right, of observation in the cluster, which has the smallest distance, average distance to all of the cluster in the cluster, all of the observation in the cluster. Right? So it is the most centrally located point in the cluster. Yeah. So medoids are similar in concept to means or centroids, but medoids are always restricted to be members of the data set. But in the k-means method, the centers or centroids are not in the data set. Okay? They are just some points in the plane. In contrast to the k-means algorithm, k-medoids chooses data points as centers, and the most common realization of k-medoids is the PAM algorithm, partitioning around medoids. Okay. Let's see how it works. So first, initialize. Okay, select k of the n data points as the medoids. Still, the initialization is random. Okay, so randomly pick 3 points as medoids first, right, from the data set. Right. Of course, we still need to decide how many clusters we need. So k should be pre-specified first. Right. And then associate each data point to the closest medoids. So still we need to measure the distance between each point and to each medoids. and then allocate or assign the observation to the closest mitoid. So this is the second step. And then the third step, for each mitoid M and for each non-mitoid data point O, swap M and O, and then associate each data point to the closest mitoid and recompute the cost or the sum of distances. So let me use a very simple example to show it and to let you better understand it. So consider a cluster with 4 points. Okay, so suppose this is the mitoid of this cluster. And these three observations are like O1, O2, and O3. And the mitoid is called M. I'll just call it M. So after the first assignment iteration is done, then swap for each mitoid and for each observation, each non-mitoid data point in the cluster, we swap them. So namely, we will make, for example, make this the new mitoid, okay? And then make this mitoid on observation, a regular observation, O pi. Okay? And then we calculate the distance between each observation in the cluster from the new mitoids. This is the new mitoids, and calculate the cost function. Basically, in this case, it's the sum of distances, summation of dj squared. So j is from 1 to, for example, n 1. Right? So that is the total number of observations in the data. So recalculate the sum of distances. Right? And if the total cost of the configuration increased in the previous step, undo the swap. Basically, we compare the new sum of square distances and the original sum of square distances when the mitoid was still this one. Okay, so compare them to. If the distance, sum of square distance decreases, we keep the swap. Otherwise, we undo the swap. Okay? So we do the same thing for all of the observations. Basically, try each observation in the cluster. Try to find a better mitoids in the cluster, basically. Okay, that is the whole process. And we'll do the same thing for other clusters. Yeah. So namely, so the main difference is the center now has to be a point in the cluster. And we do this swapping process again. Yeah. All right, now let's see how to apply the PAM function. The PAM function is in this package called cluster. Again, please install it, right, and play with the code. And feed the data set baseful. And there is an option called stand. So we don't have to scale the data by ourselves. So we can just let it be true, right? And the algorithm will standardize it. And then choose the metric. Usually we use the Manhattan metric for the k-mitoids method, but you don't have to, okay? And k equals 2, still 2 clusters. And save the result here, and we plot it. So this is the result. Okay? And we can also use Euclidean method, Euclidean distance, and see this is a result. Remember, Euclidean or Manhattan, they are just different metrics to measure the distance. But the strategy is still similar. Right? We still try to find the point that is closest to all other points on average. So in this example, no matter which metric we use, we have exactly the same result actually. You see from the index is exactly the same. Right? So for example, we can compare these two results. Right? So calculate PAM-mod 1 clustering not equal to PAM-mod 2 clustering result. but basically comparing their labels, clustering labels, and it's 0. So there's no difference between these two results. Okay. How about k-means and k-medoids? Is there any difference? So if we calculate, calculate the clustering result of PAM Mark 2 and the clustering result of k-means Mark 2. It turns out that all of them are different. That actually means they just assign the opposite labels. Remember, there is no ground truth in a clustering algorithm. There is no y variable. So the algorithm will just assign 1 and 2 to two clusters. Sometimes they may assign 1 to this one, 2 to this one, or another algorithm may assign 1 to this cluster and 2 to that cluster. But it doesn't matter actually. Turns out that they assign the labels in the opposite way. However, they actually the results are essentially the same. If you take a look at this one and this one, you see exactly the same actually. So this is a PAM method. All right. And then let's take a look at another example. The US arrest data set. So this one contains statistics in arrests per 100,000 residents for assault, murder, rape in each of the 50 US states in 1973. So it's a building data set in R. And take a look at the first few rows, 4 columns, and each observation is corresponding to one state. So totally 50 states. And apparently, the different feature variables have different magnitude. So murder has the smallest magnitude, and assault has the biggest magnitude. So it makes sense to scale the data first. We remove observations with any missing values, and then scale the data. So this is a description of the scale function. So by default, actually, center equals true and scale equals true, which means minus mean divided by standard deviation. So this is actually the default options for these two parameters. But you can choose to center it only or scale it only for other algorithms. But for clustering algorithm, the recommendation is to scale and center the data at the same time. So after we scale the data and remove missing values, we save the result in US arrests 1. See, this is the result. All of them have the same scale now. And then let's figure out the optimal K. So now we have 4-dimensional data. It's not possible to visualize it using all of the features unless we reduce the dimension to 2 first and then visualize the result. So if we don't visualize, we don't do dimension reduction and visualize the result, we don't want to guess, we can again use this function to figure out the optimal K. So now turns out that the optimal K is 2. So this is a very good example that the optimal K may not be the one that is corresponding to the biggest gap statistic, right? So this one, when K equals 4, the gap statistic is the biggest. However, this is not an optimal one. Instead, 2 is the optimal K, right? Because this is the smallest K such that it is greater than gap K plus 1 minus 1 standard deviation. This is the first time. So this one doesn't work. This is smaller than that. This one won't work. But all of these actually also greater than the lower limit of one standard deviation interval. Anyway, k is 2. Now we can apply the k-means function to do a k-means clustering. Specify 2. So this is the result. If we plot using this function. So let's see, where is Pennsylvania? Yeah, the Pennsylvania is here. Only 2 clusters. And if we use the PAM method, still 2 clusters. Same result, exactly the same result. Yeah, Pennsylvania is also here. Right. All right. Now we're done with clustering. Not clustering, this is partitioning clustering. Okay, we talked about k-means and k-medals. And we also learned how to find the optimal k using a function. And then let's move on to hierarchical clustering. So this is a different approach, very different approach. So first, it does not require to pre-specify the number of clusters to be generated. So you don't have to guess how many clusters. And the result of hierarchical clustering is a tree or a dendrogram. But this tree is sort of different from a decision tree. So remember, this is an unsupervised learning model. A decision tree is a supervised learning model. For a decision tree, the tree grows from the root, from the top, and then gradually grow downward, right? So this is a decision tree. But a dendrogram or hierarchical clustering tree grows from the bottom, from the leaves. So it will start from odd observations on the bottom and try to combine them together. And then gradually combine them together until all of the observations are in one set, which is the root. So, and trees can describe degrees of similarity between different objects, regardless of how those relationships came to be. So it will provide more information than the previous partitioning clustering. It not only provides the labels, clustering labels, it also tells you the relative relationship between all the observations in the data set. And let's see, there are 2 main steps in constructing a clustering tree. So first, represent each case as a point in a Cartesian space. So basically, it will, as I said, it will put all of the observations on a straight line, somehow like this, one-dimensional, right? And the points that are closer to each other will be put together, right? So they are actually somehow ordered, right? It's not a random list of observations. They are the distances have already been calculated. Then make branching decisions based on how close together the points or clouds of points are. So for example, naturally you will connect these 2 together and then these 3 together and then these 3 together. And in terms of distance, these 2 clusters, small clusters are similar, closer. So we'll combine them together to a bigger branch first, and then finally put them all together. So this is how we grow a dendrogram from the bottom to the top. Okay. So let's see one example. We will use the US arrest data to build a tree. So take U as a rest and scale the data first. And then we use, so this one is used to specify the metric that is used to count the distance. And so DIST stands for distance, and we use Euclidean. And then hierarchical clustering tree, H-clust. So this function is a base R function, I believe. And method equals word D2. So there are some options for this method. So this is, I think this is probably the default option. Right? And then save the result here. And then we can plot the tree. So you can see this nice looking tree. So see all of the 50 states are listed at the bottom on the straight line. And then the tree gradually grow from bottom, starting from combining two states together first. You see Alabama and Louisiana, and then Georgia and Tennessee, and then together, gradually go together. So let's see, where is Pennsylvania? Pennsylvania is here. So in terms of crime data and population data, the closest state is Ohio, which makes sense. Okay, we're kind of similar. And then the other branch is Oklahoma, Indiana, and Kansas. So all of them together. So we are kind of close in terms of crime data and population data. Right? So we are very far away from Alabama in all of these. Right? And additional information is provided by the length of the branch. Right? So for example, so you see, so these two are relatively long, which means these two clusters are kind of far away from each other. And if you take a look at these two, the length of these branches, so they also denote how far away these two branches are from each other. The longer the branch, and the more far away the two clusters or the two observations are. Okay? All right. So this is a clustering dendrogram. Very simple to create it. And of course, one restriction is that for large data sets, it will be very difficult to create a visible dendrogram. Now imagine if you have 1,000 observations, all of these labels will be clustered together. Okay, it's very difficult to tell any observation, the label for any observation. Alternatively, we can use this function to plot the tree. Right? So still, you need to fit the tree using the H-clust function. And then you can choose to use this FV's dent function to plot the tree. Right? If you use this function, you have the option to specify how many clusters you want. And then the algorithm will automatically put a border for each cluster. Right? For example, if we say k equals 2, and then you see it will automatically create separate the two clusters using this borders. Okay, and you can also choose color palettes, and yeah, so this one is used to add rectangular around groups. All right, and you can also, if you think we need 3 clusters, for example, okay, then you can just let k equal 3. Then you see the right cluster is further separated to two smaller clusters. And now we have three clusters. Right. So of course, this K should be decided by some other function or from some expertise, experience, etc. Okay, judgment. Um, but anyway, this is a way to visualize a tree in a better way somehow. So now let's move on to dimension reduction. So this is another topic in unsupervised learning, or another types of algorithm in unsupervised learning. So among the variables in the data set, some variables may carry very little information that is relevant to the task at hand. And some variables are informative but are redundant. Namely, two or more variables are giving essentially the same information. Right? For example, if you have a variable that is height, that is for example, that is the height in inches. And you have another variable which is height in centimeters. Suppose both of them exist in your data set. Then apparently one of them is completely redundant because they have a perfect linear relationship. The information contained in one column is completely contained in the other column. So one of them is totally useless. So how to control redundant or irrelevant variables? And why do we need to control them? There are multiple reasons. So first, redundant variables make it harder to learn from data because irrelevant variables are simply noise that obscures actual patterns. If you have two variables, x1 and x2 are very similar, not exactly the same, but very similar, then the difference from them is basically noise. Maybe due to measurement error or because of some other reasons that there is a difference somehow. The difference is noise. And because they are highly correlated, it will introduce a big variance in the data set. And then for machine learning algorithms, a large number of variables will present computational challenge. That's right. Yeah. For high dimensional data, the searching surface is very bumpy because if the dimension is very high, like in your searching space, then it's very likely that your training data set is very sparse. Namely, the distance between any two observations is very far away. In that case, you can imagine if you have a new observation, it's very difficult to do a very good prediction. And also the algorithm itself is very difficult to converge. Just because the searching surface is too bumpy. So all of these motivate us to reduce the dimension. So let's first take a look at the iris data set. So it has four feature variables, the length and the width of sepals and petals in centimeters. Let's take a look at the relationship between petal length, petal width, and sepal length. The first scatter plot shows you the relationship between petal length and petal width. Okay? So there is a very strong linear positive relationship between petal length and petal width, which means the information that is contained in one variable is also contained in the other variable. Okay? And also petal length and sepal length, there is also a moderately strong linear relationship between these two variables. So from this two scatter plots, we know that the variables in the average data set are highly correlated, which indicate that some variables are redundant. It may not be necessary in building a model. We actually have seen this before. We use all of the variables to create a decision tree, but in the end, only two variables are used, right? And two variables are not used at all. Were not used at all, right? That's because those two variables are not necessary. Right? They are redundant. So the strategy we use to reduce dimension is principal component analysis. So this strategy uses an orthogonal transformation to convert a set of observations of possible correlated variables into a set of values of linearly uncorrelated variables called principal components. So basically, we create some new variables using existing variables. And each new variable is a linear combination of our X variables. So let's first take a look at some notes about this algorithm. So first, how many new variables can we create? If there are n observations with p variables, so our data matrix, suppose, is like this. So n rows and p variables. Then the number of distinct principal components is the minimum of n minus 1 and p. By the way, the principal components is a linear combination of all variables. So this is a new variable, right? So don't be confused. It's just a new variable. So the number of distinct new variables is the minimum of n minus 1 and p. So usually, n is greater than p, right? Usually, there are more rows than columns, right? For regular data set. In this case, you can create p distinct principal components. P distinct principal components. But if n is smaller than p, smaller than or equal to p, then you can only create n minus 1 principal components. So that is because the number of distinct principal components depends on the overall degrees of freedom in the data set. So that is usually the smaller dimension of the data set. And let's continue. The first principal component has the largest possible variance, or in other words, it accounts for the largest proportion of variability in the data. So it contains the most information, the most amount of information in the data set. And each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding components. So let me use a plot to show you this idea. Suppose we have a data set like this. A cloud of data like this. This is X1, so two-dimensional data. Then consider we want to project the data to a one-dimensional space, to a line. Then we need to pick a direction such that the variation of the data is maximized. Okay? It retains the most variability in the data set. From this plot, it's very obvious that the best direction is this one. So if you project our data to this line, then they will be like this. If we use a rock plot to show it, it looks like this. So apparently, this the observations on this line has the largest variance or spread. So this will be called the first principal component, the first principal component. And then we need to find another direction such that the projected observations has the second largest variation, or explains the second largest proportional variability in the data. And another restriction is it has to be orthogonal to the first principal component, first direction. So since we only have two-dimensional data, we have no other choice. So the other direction must be this. And if we project our data to this direction, we have a log plot like this. Okay. And they must be orthogonal. Orthogonal. So this is PC1, and the green one is PC2. And apparently from this plot, we see that both PC1 and PC2 are linear combinations of x1 and x2. Right? And they are orthogonal with each other. And PC1 always explains the most proportion of variability, and PC2 explains the second largest proportion variability. If we have more than the first, so the amount of variation explained is always in this order. And the last one is the least important one. So it's always like this. Okay. And the resulting vectors are an uncorrelated orthogonal basis set. Okay. So the other new variables, the principal components, are uncorrelated. Okay. And from this calculation, you know that PCA is sensitive to the relative scales of original variables. Okay. Consequently, we usually need to scale the data first, right, before we apply the PCA algorithm. Okay. So apparently, principal component analysis is useful in dimension reduction. It also, in particular, is often used to do visualization, right? Because we only can have 2 or 3 dimensions. If we want to create a plot, right, we can only use 2 or 3 variables. So it's widely used in data visualization. Okay. Now let's examine some details of principal components analysis. The PCA creates new variables, PC1, PC2, etc. And each variable is a linear combination of existing variables. For example, take a look at PC1. It can be denoted as phi11x1 plus phi12x2 all the way to phi1pxp. So notice that each coefficient, each slope has 2 subscripts. The first subscript is corresponding to the index of the principal component. Now we see 1, 1, 1, 2, 1p. And the second index subscript is corresponding to the x variable, the index of the x variable. So from this, you know that for each principal component, we have a set of slopes of bi1, bi2, all the way to bip. Yeah. And the algorithm actually will return this vector of coefficients or slopes. Right? And in order to define a unique vector for each principal component, we require that each vector of coefficients or slopes has norm 1, namely sum of phi1j squared has to be equal to 1. Sum of phi squared must be equal to 1. Right? Otherwise, if we only consider direction, right, it's not unique, right? The direction only describes the relationship between x1, x2 all the way to xp, but it's not unique. But by restricting, put a restriction like this, the principal component is kind of like fixed, right? Somehow fixed, or you can say it's unique along each direction. So geometrically, PCA amounts to a rotation of the coordinate axis so that more of the variability can be explained using just a few variables. So in the previous example, in the plot, I show you the two principal components are like this and that. If you rotate the entire data using, namely, if you let PC1 be parallel with the x-axis and PC2 to parallel with the y-axis. It's essentially a rotation of the coordinate system or the axes. And then you can choose to discard some principal components. For example, in this case, we may choose to discard the second principal component because it's relatively smaller. And suppose we only want to use one-dimensional data, okay, then we can get rid of PC2. And PCA is an example of linear dimension reduction, okay, because you see each principal component is a linear combination of x variables. All right, let's take a look at the iris data set. As I said, we need to scale the data, right, because the distance is sensitive to the magnitude of variables. Not the distance, is the calculation of the slopes in the principal components is sensitive to the magnitude of variables. So let's deselect species, the response variable, and apply the principal component function prcom. So this function is a base R function actually, and then specify scale equals true. Then the data will be scaled. And then take a look at the rotation component in the result. Okay, we see the result in PC iris. So these are actually the coefficient matrix. Okay, the slopes. Okay, the slopes for each variable. Okay. So for example, PC1 is equal to 152. So this one times sepal length, and this times sepal width, this times sepal petal length, etc. Right? And then given the values of one observation, sepal, given these values, then PC1 has its own value. Right? So namely, is a complete transformation of the original data set to a new data set. So originally we have four variables, right? X1, X2, X3, X4. And we have a lot of observations from 1 to 150, for example, for the iris data set, right? And after we apply the PCA function and calculate the principal components, we will still have four principal components. Okay. So four new variables, still 150 observations. Okay. Just each variable is a linear transformation of the previous variables. Okay. And now all of these principal components are orthogonal with each other. They are all uncorrelated. And also they are ordered in terms of importance. PC1 is the most important, and then PC2, etc. But all right, let me see what else. Okay, then let's see the result. let's plot the first two principal components, okay, for the iris data set, and we map species to color. So you see, this is the true labels and the first two principal components. And for comparison purpose, we also map the clustering labels to the plot. So you see the difference between the true labels and clustering labels. But anyway, so this example shows you that PCA is a strategy to reduce the dimension of data and create visualizations. Okay. All right. I think I will stop here because the next example is a more advanced example, and we only have 4 minutes left. I will continue tomorrow. And I will email you about your quiz 4. The last quiz is still about supervised learning. There's nothing about unsupervised learning. However, your exam 2 will cover unsupervised learning. So I suggest you to practice all of these examples and make sure that you are familiar with these algorithms as well. All right, any questions? All right, hello everyone. Welcome to today's class. Today we will finish the last topic, principal component of analysis in the last module, unsupervised learning. And we will see another example of clustering. Use clustering strategies to solve a problem in practice. Okay. Let's see. Principal component analysis. The last time we introduced this method. So this PCA is used to reduce the dimension of a data set. Okay. So basically, this PCA analysis will create new variables using existing variables in the data set, X variables. And those new variables are linear combinations of existing X variables. And the principal components, each variable is called a principal component. So I will label them in this way, PC1, PC2, etc. Okay. And if there are n observations in the data set and p variables, and then we can create the minimum of n-1 and p distinct principal components using the data set. It really depends on which number is bigger. Okay. And so suppose p is smaller than or equal to n-1, then we can create these many principal components. Okay. Each one is a new variable, which is a linear combination of existing variables. Okay. And they are ordered in terms of importance. Right? Namely, the first principal components contains the most information in the data set, right? The most amount of information or percentage of information in the data set. And then the second principal component contains the second largest amount of information in the data set, etc. And the last one contains the least information. Right? And also, all of these principal components are orthogonal or uncorrelated. So they are just geometrically orthogonal with each other, right? The directions. Okay. And the last time we talked about the construction of principal components. So each principal component is a linear combination of X variables. Okay. And also the coefficient vector is normalized, which means the norm is equal to 1. So this is another restriction about principal components. So let's see another example. This data set. Yeah. So both from Scottish Parliament. So this is a very wide data set after data transformation. So consider votes in a Congress in the Scottish Parliament in 2008. We know that legislators often vote together in some pre-organized blocks, for example, political parties. And thus the pattern of ayes and nays on particular ballots may indicate which members are affiliated. So this is kind of an expectation. I will know that politicians vote according to their party, a political party, usually. And let's take a look at the data set first. We can use this structure function to take a look at the overall structure of the data frame. So it has 103,000 observations about, and the three variables only. The first variable is the bill, the name of the bill. And the second variable is the name of the legislator. And the last one is the vote, either 1 or 0 or -1, which represent yay or nay or abstain. These three values. So this is actually a very long, very narrow data frame originally. However, suppose we want to answer one of the following questions. For example, can the members of parliament be grouped according to their voting patterns? So if we answer this question, we want to answer this question, then the unit should be each member in the Congress. In other words, each row should contain all the information about one legislator. Apparently, our original data set is not like that. So each row is corresponding to the voting result of one person on one bill. So consequently, because each person will vote on all the bills and there are many bills, so this is a kind of this is in a different structure. So in order to answer our question, we need to transform this data set into a wider data set. Namely, we want to make it wider and so that each row represents or contains all the information about one legislator. In order to do so, we can use the spread function in the tidyr package. We have learned this before in the data wrangling module. So we can take the votes data set, the original data set, and apply the spread function. And we will use the values in the bill variable as new variable names. So use it as a key variable. So each bill will have its own column. And the vote variable will provide the values in the new table. And so basically 1, 0, or -1. And then make it a table. And after the transformation, we name the data frame y.votes. Now take a look at the dimension. So now it only has 134 rows and 774 columns. So it's a wide data set now. So this is the number of members in the Congress. And there are 773 bills. The first variable is the name of the legislator. So take a look at the first few rows of the data set, of the wide data set. So each row is corresponding to one person, and the column name is the bill, the name of the bill for all of the 773 bills. Okay. And in this case, if we want to use PCA to reduce dimension, the question is how many distinct principal components can be created using this data set. So remember, the rule is we can create the minimum of n-1 and the p distinct PCs, right? So now n is apparently smaller than p, So we actually can create 133 distinct principal components instead of 773. And we can only create this many principal components. Okay. All right. So before we start, let's create a tile plot to see if there is any pattern in the data set. The x-axis is corresponding to different ballots or the different bills, and the y-axis is corresponding to different members of the parliament. So apparently there is no pattern. We cannot tell any difference, any pattern from this plot. It's kind of like a carpet. And how about PCA? PCA can be used to create visualizations, can be used to reduce the dimension and then create visualization, right? So let's try to use PCA to reduce dimension to 2 and then see if we can figure out how many clusters are in the data set. So we'll first remove the name column and then scale the data, although it is not really necessary in this case because all of the values are 1, 0, or -1. So it's not really necessary, but anyway, it doesn't hurt. Right? Save the result here. And then, so since we didn't specify how many components we need, it will actually create 133 principal components for us. And then let's select the first 2 principal components and the name from the result. By the way, the X component of the output of this function contains the principal component values, the values of the new variables. Okay? So previously, last time, when we did an example using the iris dataset, we only took a look at the rotation. The rotation contains the coefficients, those Vij's in the formula, the coefficients. For example, so this is the first 10 coefficients of the first principal component. You see the first column, the rotation, first column, the first 10. So totally, actually, there are 133 V1Js, right? Totally 130. Yeah, because we have, no, sorry, actually not 133. Actually, there are 733. Yeah, 700. See, sure. 773 Vijs. 773 Vijs actually. Okay. For each principal component. Okay, we just show the first 10, okay, for the first principal component. And these are the first 10 for the second principal component. Okay. And the X matrix actually contains the values of those new variables or principal components. Right? So see, we pull out the first 2 principal components, right, and show the first 6 values. And then let's create a scatter plot using the first 2 principal components. So it looks pretty good. We can see clearly at least 3 clusters in the data set. Okay, 1, 2, 3. Potentially there are more clusters over here. Okay, so apparently the voting results are clusters according to something unknown for us yet. And let's first use k-means, the k-means method to cluster the data. For example, we know that there are 6 public parties in the country, the 6 national Scottish political parties in the country, but there is one more small party somehow. So totally we will use 7 centers in the k-means function. And then we create a new variable called cluster. So this one contains the clustering labels. right? And then use a mutate function to add it to the principal component matrix, right? And then we create this scatter plot, map the classroom label to colors. As you see, pretty good, the result, okay? So, which means the clusters are kind of, yeah, we can actually visualize those clusters using the scatter plot. Okay. And then let's compare the clustering labels with their true parties. So actually, we have a separate data set which contains the party information of all of the legislators, right? That is contained in this data set called parties. Right? So we can mutate, right? We can use the left join to join these two data sets. One is the vote data set, and the other one is the party data set by name. And then we create a contingency table of the clustering labels and the true party status. Of course, we know that the clustering algorithm does not know the ground truth, so it can never assign true labels to those observations. It will only assign integer numbers. So you cannot just focus on the diagonal of this contingency table anymore, right? Instead, we just focus on each row and see whether or not most of the observations are clustered into one column. Right? And if that is true, then the program is good, right? The algorithm is good. Right? For example, take a look at this party, Scottish National Party. So 35 out of 36 members are clustered to cluster 1. Similarly, this one, 15 out of 17 is clustered to the fourth cluster. So the result is pretty good, pretty good. Although, remember, the k-means method is an unsupervised learning algorithm. It does not have any information about the target value, but the clustering result is good. So the expectation is true. Those politicians actually vote based on their party. Yeah. Basically, they vote in blocks. And then how about so let's see. Suppose we don't know how many clusters we need. Right? Let's see how many clusters we need using the first 10 principal components. Of course, we can just directly feed the entire data set into it, but it might not be a very effective or efficient idea. So let's just select the first 10 principal components and save it in PC10, and then use this function to identify the optimal number of polys, clusters. So turns out that optimal k is equal to 5. Although actually there are 7 different parties. But from this table, you see that some parties are very, very small. So you see the first one only has 1 member, and the third one also only has 1 member, and the last one has 1 member. So basically these 3 are either outliers, or the algorithm, the function probably put them together or put them into some other clusters. So optimal is 5 based on this gap statistic. And then let's fit a k-means model using center equals 5. Then we have, this is the result. And supervised, actually principal component analysis can be used in supervised learning models. They can be used to pre-process the data requirement, those to reduce the dimension of a very wide data set, and then we can feed those the first few principal components into a supervised learning model and do prediction for the y variable. So for example, let's fit a decision tree model on the both data set. So we first do the following. We select the first 10 principal components, and then save it here. And then we will just use it to put a decision tree. We call it votes.data. And then we split the data to a training and a test set and fit a decision tree using a training set. And then calculate the misclassification rate for the test set. It turns out that the misclassification rate is very small. It's about 7.4%. Okay. So this means actually the first 10 principal components contains a lot of information. Right? There are actually, remember, actually there was 773 columns, right? Except for the first column, there are this many columns. Right? And we reduce it to 10 columns and then use it to fit the decision tree model. The result is pretty good. All right. This is how to use PCA in the supervised learning model. So you can use it to reduce dimension. And then another very important topic. We know that after transformation, each principal components contains a certain percentage of variation in the original data set. And they are ordered in this way. PC1 is greater than PC2, is greater than all the way to the last one. In the sense that the first one contains the most information, the second one contains the second. And how to calculate this kind of percentage or level of importance. So actually the this function, the PR comp function, actually returns some quantities or statistics that can help us to calculate that. In particular, it is a standard deviation component. So this one sort of contains a standard deviation for each principal component. Suppose for our both data set, we can create 133 principal components, right? And then this vector SDEV will contain 133 values. It's a vector of this length, 133. And then we square it and then divide it by the sum of it. We can, so this quantity is called proportion of variance explained. Proportional variance explained. Right? Because we sort of normalize it, the sum of them, the sum of PVE is equal to 1. This factor is equal to 1. And let's take a look at the first 10 principal components, the PVEs. So you see the first principal components contains about 53% of the information or variation or the variance in the data set. And the second component contains about 20% of the information. So if you add them together, so the first two principal components contains about 73% of information already. And this PVE decreases along the index. And so first 10 add together, it's a lot already. And we can actually visualize the PVE, the change in PVE. So this is the plot is called the streak plot. It's kind of just like a scatter plot, connect the scatter plot for the number of principal components, the principal component index, and PVE. For example, this is a plot for the street plot for our votes. data set. And of course, there are actually 133 principal components. We can create a very large, very wide plot. But because we know that only the first few principal components contain most information, so we just pull out 15 of them and create a plot so that each point is bigger. And notice that at a certain point, PVE dropped a lot, right? Which means the PVE of a certain principal component suddenly dropped a lot. For example, PVE4, compared to PVE2, PVE3 is significantly smaller. So this point usually is called an elbow in the screen plot. So this indicates probably the optimal number of principal components you need. But it's not necessarily, it is not always true. Okay, pay attention to that. So let's see, you see PVE3 is only 2%, 2.3%, and PVE2 is still 20%. So indeed, there is a big drop at 3. So this is where this elbow is located. Okay. But this is this can use as a reference, but it may not be very precise. It may not always be very reliable. So pay attention. A more reliable way to visualize the result is to create this cumulative proportional variance explained plot with this kind of plot. Yeah. So for example, so let's enlarge the x-axis. We can consider the first 50 principal components. So now we put out the first 50, and PC is from 1 to 50. Okay. And then we create a scatter plot for the number of PCs and the cumulative sum of PVE. This cube sum function, remember, will not change the dimension of a vector. It will keep track of the cumulative sum. For example, if you have a vector like 1, 2, 3, 6, etc., then the cumulative sum will be 1, 3, 6, 12. So it's after you apply the cum sum function, the length will not be changed. It's still a vector. Okay. And that is exactly what we need. We want to keep track of the cumulative sum of the overall PV for some number of principal components. So take a look at this plot. Turns out that and I add a reference line, which is y equals 0.9, which indicates the 90% overall variance explained. Okay. So it turns out that you need to use at least 37 principal components in order to explain at least 90% of the variation in the data set. So namely, if I only want to lose 10% of information by reducing the dimension, then I need to use at least 37 principal components. Compared to the original width is this. So it's already very good compared to this many, 773 to 37. It's already a big reduction, actually. All right, so this is a cumulative PVE plot. It's very useful for us to determine. Alternatively, we can use this function. We first calculate the cum sum. So this call it CPVE, cumulative PVE. And you can apply this which max function on this logical vector. CPVE is greater than or equal to 0.9. CPV is a vector of numbers, values, and then we compare it with 0.9. So the result is a bunch of is a vector of true or false values. So you can imagine it's somehow like this, and all of a sudden, from the 37th number, it becomes true because the cumulative PVE is greater than greater than 90%, right? 0.9. Right? And then this weight max function will return the index of the first max value of a vector. False in R is equivalent to 0, and true in R is equivalent to 1. So the first max value is the first true. The index of the first max value is the first true, and the index is 37. Okay, so this is that's why we can use this function to identify the first time that the cumulative PVE is greater than or equal to 0.9. Right, so this is the first time the max value occurs. So it's 1. Yeah. All right. So that's all for principal component analysis. And very important thing is to really understand the strategy and the properties of principal components and how many distinct principal components can be created using a data set. It depends on the dimension of the data set, the shape of the data set. And also we learned how to calculate this PVE, proportional variance explained, and how to select the minimum number of principal components so that about like most of the information can be explained still.